To kick us off today, I would like to welcome Alexey Aleyev, Data Science Lead at Grid Dynamics, and Vasily Kovalchenko, Data Scientist at Grid Dynamics. They will talk about building a personalization platform using reinforcement learning. Throughout the event, you can view presentation decks within the console resources icon. Drop your questions in the Q&A panel and we will answer them at the end. With that, I will turn it over to Alexey.
Hello everyone, thank you for attending our session called the Plug-and-Play Personalization Platform using Reinforcement Learning. As you may know, personalization and recommendation models are widely adopted by technology and entertainment companies as highly efficient tools for digital experience improvement and conversion optimization. However, the traditional model development and productization process requires significant engineering effort that increases the time to market and implementation costs. In these sessions, we'd like to share with you our experience of building a personalization platform that reduces the implementation complexity and improves the quality of recommendations using reinforcement learning. A couple of words about us. My name is Alexey Aleyev, and here is my co-presenter, Vasily Kovalchenko. We are from Grid Dynamics, and we worked on Java-based web applications, backend services, search systems, and switched to ML projects some time ago. And currently, we are focusing on the application of reinforcement learning techniques, and we've been working together on building the personalization platform we are going to talk about. Our agenda for this session is the following. We'll describe the scenario where we need to build a personalization platform, and we'll define requirements for it. Then we'll describe the motivation behind the usage of reinforcement learning for the stated problem. We will discuss the design of a personalization platform, cover some technical details, and make conclusions regarding the overall approach. So one of the popular industries is a game dev, and typically companies not only want to make a good product, a good video game or mobile application, but also to make more profit from it using different ways of monetization, like paid accounts, game upgrades, advertisement, or in-game purchases. It will allow them to develop new games and all that jazz. So we will consider the scenario where a company uses in-app or in-game shop as a way of monetization. The users are able to purchase different products like virtual currency packs, character skills upgrades, auxiliary items, and so on. But it may be not enough just to provide the users with a way to purchase items. The users may not know about particular items if there are too many of them, or the items may look too expensive for the users initially. So one of the highly efficient approaches for improving user engagement and in-game monetization is building a platform which can assign personalized offers and promotions to the users. In fact, the same is applicable for the case of, for example, a mobile application for a restaurant. One can use offers, promotions, and notifications to improve the conversion. So we consider the case of a company that develops either mobile application or video games, where the users are able to purchase items in the application or in-game shop. And we want to improve user engagement and in-app or in-game monetization by incorporating the personalization platform. The target metrics may vary. We may want to increase offer acceptance rate or in-app user spend to make more revenue, or we may want to increase duration of game sessions to tempt users towards purchasing a new version of the game in the future. So let's talk a bit more about what we're trying to achieve by incorporating the personalization system. Generally, the relationship between consumer and brand evolves over time, and there are different stages of this evolution. Initially, if the brand does not interact with the customer, the initial goal is to acquire a new customer and give him some incentive to try a new product. In that case, the company would be interested to do some sort of acquisition or trial campaigns. Once a consumer starts to interact with the product, the goal is typically to increase consumption to make the person buy more frequently or buy larger quantities of the product. And there will be different types of promotions and offers at this stage. Finally, the interaction can decrease and the customer can decide to stop buying the product. And in this case, the goal will be to run some sort of retention campaign and target this customer with some retention offerings and discounts. On the shown plot, the black curve represents the customer spendings on the product without receiving promotions and offers. And the red curve represents the customer spendings in case of applying these marketing campaigns to the customer. So we are interested, obviously, in having such a personalization platform which will make the red curve higher than the black one. And from the business perspective, the primary goal of the company is to improve the long-term performance of the application or game, because most users interact with the product over a relatively long time span. So it is important to optimize each action, offer, promotion, or notification in a strategic context as opposed to optimizing actions in isolation. Having said that, we can formulate the requirements for the personalization platform. The platform must be flexible in terms of defining the value metrics because they may vary. The platform must provide the ability to strategically optimize the sequences of actions. New trends in user behavior may appear, and the models should be able to adapt to the changes in the dynamic environment. We're also interested in minimization of the effort and time associated with the solution implementation and the operationalization, because if we will wait for a long period of time to gather the data and build kind of a perfect model, it can lead to having a huge regret while the current offerings are assigned in not optimal manner. And many traditional marketing analytics and personalization methods use predictive modeling to score customers. The typical problem with this approach is that marketers struggle to choose the right action when they have multiple scores. And there is a lot of interest in prescriptive models that recommend a specific optimal action with regard to a certain outcome. We can note that each of the phases we mentioned previously can be translated into some supervised learning problem. And we can use propensity scoring and build, for example, lookalike models or use collaborative filtering. But they generally require to put significant effort into feature engineering, model development, and productization for each use case. In particular, some effort is usually required to operationalize the scores produced by predictive models and develop transactional decision-making components on top of them. Also, traditional personalization methods typically focus on immediate, myopic outcomes, such as improving click-through rate, but we're interested in building long-term relationships with customers, so they take optimal marketing actions within their strategic context. Thus, we would like to propose an alternative approach using reinforcement learning techniques. So let's start with a brief description of what reinforcement learning is. The reinforcement learning problem is meant to be a straightforward framing of the problem of learning from interaction to achieve a goal. The learner and decision maker is called the agent, and the thing it interacts with, comprising everything outside the agent, is called the environment. These two abstractions interact continually, and the agent selecting actions and the environment responding to those actions and presenting new situations to the agent. The environment is typically stated in the form of market decision process and is responsible for providing the reward on taking action and moving to a new state associated with the transition, ST, AT, RT, and ST+1 in our case. The agent has a policy. A policy defines the learning agent's way of behaving at a given time. And roughly speaking, a policy is a mapping from perceived states of the environment to actions to be taken when in those states. The purpose or goal of the agent is formalized in terms of a special reward signal passing from the environment to the agent. At each time step, the reward is a simple real number, and informally, the agent's goal is to maximize the total amount of reward it receives. This means maximizing not immediate reward, but cumulative reward in the long run. So a reward function or reward signal defines the goal in a reinforcement learning problem. And the reward signal indicates what is good in an immediate sense, but also we have a notion of value function, which specifies what is good in the long run. And roughly speaking, the value of a state is the total amount of reward an agent can expect to accumulate over the future, starting from a particular state. So the interaction between the agent and the environment may end at some point with moving to the terminal state. And a sequence of results and transitions forms an episode, and the agent tries to maximize the cumulative reward over episodes. In case of interaction between the agent and the environment is infinite, we say that this is a continuum task. And typically, in order to calculate the cumulative reward for continuum tasks, we need to incorporate discount factors for the later rewards. The agent has to exploit what it already knows in order to obtain a reward, but also it has to explore in order to make better action selections in the future. The dilemma is that neither exploration nor exploitation can be pursued exclusively without failing the task. And the agent must try a variety of actions and progressively favor those that appear to be the best. So let's take some examples. In the first one, the objective here is to apply forces to a cart moving along a track so as to keep a pole hinged to the cart from falling over. A failure is said to occur if the pole falls past a given angle from vertical or if the cart runs off the track. So the pole is reset to vertical after each failure. And we can have, for example, rewards as +1 in case every time the failure did not occur, for example, and treat it as an episodic task. Also, another example is from Netflix, where they recommend different artworks of the same TV series. to the users in order to maximize the conversion, the number of customers started to watch this TV series. So now let's describe interaction between the personalization system and the customer in terms of reinforcement learning. So the user interacts with the application or game and purchases items. We will define the state as a customer feature vector with features like origin country, the number of games played, total amount of spending, etc. Given the state S1, we take an action A1, which can be promotion assignment or decision not to offer promotion to the customer, and the reward can be calculated, for example, as the amount of spending until the assignment is finished. So it may not be the immediate in time, but it may be calculated only after a few days when we realize that the user is not interested in the assignments or the user consumed the assigned promotion. Then we can form the next state gathering the customer features and take the next action. And the sequence of the assignments will form a customer trajectory or the episode. The interaction between the user and the system may be infinite in theory, so we can either define a continuing task and use discount factors for rewards, or we can artificially limit the episode with particular length and form several episodes for the same customer. For example, we could form an episode with states from S1 to ST and a separate episode with states from ST to ST plus 1. The goal will be to take such actions which will maximize the cumulative reward, which can be LTV or return of investments in case of defining the reward function using the customer spendings. And having such customer trajectories, we can choose a particular reinforcement learning algorithm to estimate the value function, which will maximize the target metric and will be used to optimize the agent's action policy. So now we can see that if we will use our reinforcement learning techniques to build a personalization platform, we will satisfy the majority of requirements we formulated. Flexibility in defining the value metrics can be achieved by defining different reward functions in the environment. Reinforcement learning agent maximizes cumulative reward over the long run, so the action policy will strategically optimize the sequences of actions. Also, RL agents are able to learn continuously and use exploration, so the agent can adapt to the changes in environment. And the RL agent's policy defines the action which should be taken for a given state. The approach is prescriptive, not predictive. The remaining requirement is to minimize the efforts on solution implementation and productization, and we will address it by describing the proposed platform design and technical solution. So I'd like to give the floor to Vasily to talk about it.
Okay. After discussing the theory, let's talk about the architecture design. We have the application game server, events fly from it and are added as logs. The logs should contain trajectory ID or episode ID. For example, if you and I play online poker, the trajectory ID will be the game number. In personalization, the trajectory is the time period in which we observe the player. Event sequence number inside trajectory. Sequencing is important for learning. State vector. Player's features. His description at the moment. Session duration, amount of money spent earlier, and other activities. Action. The variant of the promo, notification, offer that the player received. Action probabilities. The probability of choosing this action. Every time the system makes a choice, it can make an exploration, and the action probability is an indicator of this exploration. Let's say we have 10 promotions and the clue is number 1. Then number 1 will have a probability of, for example, 90%, and all other than 10%. Reward. Calculated reward, a piece of the LTV or ROI that were discussed earlier. Logs in this form are sent to the personalization platform where new policy is learned, is evaluated, and the results of the assessment can, for example, be visualized for further analysis. New policies that are agents from RL terms arrive at the targeting server, which makes new prediction, and they are sent to the game server. I would like to note that the game server, personalization platform, and targeting server are decomposed with all the resulting decomposition bonuses. The platform data scientists do not interfere with the game developer's lives, and the targeting server can be scaled up to achieve a given level of performance. Now let's talk about the possible implementation that we propose. Game server, I believe you know how to write. Log is a cloud database, and our offer for personalization platform is a Facebook's framework called Reagent, which is deployed in the cloud. More about it in a minute. The place for storing models is a cloud storage. The targeting server is cloud instance, which can easily be scaled up. Evaluation results are collected and can be viewed by TensorBoard, which is already built into the reagent. Let's imagine that we are starting a new project and we have the logs of some rule-based system that marketers have built on if-else rules. And the problem arises that we do not have an action probability because the probability of if-else system output equals 100% or 1. Then we convert the logs from the rules-based system without action probability into the reagent logs, do the first run without policy evaluation because it doesn't work without the action probability, and then start the cycle using the game server logs. Let's say we don't have a rules-based system and logs at all, but someone came up with the promo options. Then there is an option to run an agent with a random policy. Perhaps at first such an agent will not make a profit, but it will be able to learn from the results of its work and adjust the policy. And if there is enough data, the agent can reach a profitable policy relatively quickly. Then we start the first run of the system with a random policy. That is, each action can be selected with equal probability. And then we start the cycle. The main thing is that in both cases, when there is no system and without it, the same flow is applied. Let's talk about details about reagent. If your infrastructure allows, then you can run the online policy training supported out of the box. That is, learning during runtime. And you need to understand that policies, agents, models are computationally complex and are often calculated in online training, which can become a rather expensive system. Therefore, there is a second implemented method, the offline policy training, called RL batch, better supported as it is used more often for economic reasons. As you may have noticed earlier in the architecture diagram and its implementation, it was about learning cycles. The harness for starting training loops is built quite easily from the reagent toolkit because the guys did a good job and it was decomposed as it should. Different RL algorithms are supported for both online and offline training. There is a support for exploration exploitation with different sampling strategies. On-policy and off-policy training is supported. Unfortunately, we don't have time to dig into details, and please learn about it later if you'd like. A mechanism for evaluating a policy, comparing it with other policies, policy evaluation, CP, counterfactual policy evaluation has been implemented in reagent. There are some restrictions on policies that can be compared, and there are places that need to be fixed to take off, but it works. Policy training can be accelerated with Spark support. And here we are talking about the fact that the states need to be preprocessed, and this can be given to the Spark. Okay, after discussing, let's summarize everything together. And first of all, from our experience, it not only works, but also brings in more revenue than a rules-based system. After n cycles, you receive the agent that is a policy, that is a neural network that can predict for any player, the old one or newcomer, the such promo that leads to maximum profit in the long run. Start up the system relatively quickly. It's not completely plug and play, but it's still a significant step forward from trying to build your system from scratch. The platform provides automation out of the box for policy evaluation, for A/B testing of policies in production, various RL algorithms. Taken together, this provides an opportunity to focus on developing the main target metrics, the reward function in particular, developing an appropriate definition of episode in your case. In the traditional ML approach, you will also need to think about this, but besides this, you will also need to solve all the tasks solved by the platform. And as you can see, it can be applied not only to the game industry. That is, for an abstract McDonald's or Pizza Hut apps, we also have user description, that is features and promotions or offers. Thank you.
Thank you for attending our session, and we will be happy to answer your question.
Thank you, guys. Well, we're very excited. We've got some questions from the audience, so let's get started. First question is, could you please elaborate on how the episodes can be formed in your case?
Thank you for the question. Yeah, so regarding the episodes in our case, let's again consider two scenarios where we have historical data and we don't have it. So in case we have historical data, define the target metric, and for example, we would like to make such recommendations which will be optimal for the next year, for example, or for the duration of the whole year. Then it means that we need to compose episodes with recommendation assignments for the whole year for all the users, like whatever data we have. And so the agent will try to learn from this historical data and come up with a policy which will be optimal for different states of the user feature vectors for the long run of the whole year. And in case we don't have historical data, like for example, we may have a new release of the game, users just started to play, then we can make several assignments, for example, with a random policy, or if the new version of the game is similar to the previous one, we can either try to start with some previous agent, but let's imagine we started from random one, and we just combine a couple of assignments, and we will form episodes, several assignments, like it may be calculated in the number of assignments or for a particular period of time, like 2 weeks, then for 1 month, then for several months, etc. So the more data we will have, the longer episodes we will form. And we will start from the short ones, and the agent policy will try to optimize the recommendation assignments for this short period of time. Then we will deploy the agent into production. It will work for some time, and we will have more data. For example, for 2 months or 3 months, we will then gather all this historical data once again and form longer periods, longer episodes. So the agent will evolve over the time to optimize the strategic behavior for the longer and longer periods of time. So that's one of the approaches. And also, if it was mentioned, we may treat the interaction with the user infinite interaction, like because typically if the user will play the game for several years, then we will have a lot of assignments, etc. And one of the approaches is to form the whole trajectory with all the assignments, but just make a discount factor for the later rewards. So we will limit the overall cumulative reward. And another approach is to have a sliding window. For example, if we will work on the optimization for the assignments for the several months, then we will get the historical data for specific users for these several months. For example, from the assignment number 1 to assignment number T. Then we will form the next episode for the same user, starting from the assignment number 2 to assignment T+1, then from assignment 3 to assignment T+2, etc. So we will have a sliding window with the episodes of the same length. And the length may be, the episode may be formed in terms of the number of assignments, or it may be treated as the period of time, like several months, and whatever number of assignments we will have for these several months, etc. So that's it. That's our approach.
Great, thank you. I think we've got time for just one quick additional one. Have you tried to implement the solution using other RL frameworks?
To be perfectly honest, we haven't tried to implement the production version of some problem solution using different RL frameworks. We just tried several frameworks with the toy environments, like the cardboard problem we've mentioned in the session, etc. Because, when you work with the customer, then typically you don't have enough time to implement several solutions in parallel and compare them with each other. So we've used Reagent because it is supported, like it is actively developed by the Facebook research. And the guys from Facebook already have some experience with building recommendation systems using this framework. So we thought that it will be a good solution. You can try other frameworks like RLLib from Ray project. It also supports several algorithms, and basically it has similar functionality. And also, if, for example, you are working not with recommendation systems, but, for example, with games, then you want to learn some agent which tries to play the game the best, then you may want to look at the CDRL framework by DeepMind, because they use it to develop the agents for playing in games like StarCraft, etc., and they have great results. And CDRL is basically optimized for distributed